Good afternoon. My name is Rixin. Thank you for your coming, and I'm very proud to discuss the topic about characterizing the CSC operation on Ceph. So why we need CSC? CSC is short for the cyclic redundancy check. It can use to detect network data error or the disk data error. For the modern CPU, they also have the special instruction to accelerate the CSC operation. During the test, we can see the CSC. During the test, we test run the read or run the write. We can see the CSC is a hot function occupied the CPU utilization is about 3%. So if we know how the CSC operation is executed in Ceph, so it can help us to do the better optimization. There is two threads execute the CSC operation. The first one is the message worker. The second is the TBOCD DB threads. The message worker always receive the message from the client or the OSDs and send the reply to the reply. So you can see in the picture, the message always has three parts: the preamble, the payload, and the epilogue. So preamble saves the payloads, how many segments the payload has, and how long the payload segments, the payloads segments length size. So we can see the payload it always has four segments. The first segment is a header, is a Ceph message header, and the second is the front part. It tells us what the operation the message will do, and the middle part is not used for now, and the last is data part. And the Bluestore will calculate the CSC while read and write to make sure the data is correct. And there is three related config in the Ceph. It can directly influence the behavior of the Ceph. So we analyze the workload. We just use the mass-work v2 protocol. We use FO to launch the RBD workloads. We test both read and write, and we test both small size 4 kilo and the multi-peak size 64 kilo with replica 1 and 3. And we used the Bluestore to as the backend store. So we used the BCC trace tool to count the function Ceph CSC function about 2 million times, and we get the size of CSC operation data block size. Here is the result we found. As you can see, the right picture, yeah, there the x-axis is the size of the CSC operation, and the left y is the count of which size CSC operation do, and there is right y-axis is a calculated distribution function. The maximum is 100%. So we first analyzed the master work threads for 4K run write. We can see here, this value is not cannot see. It's 8%, 84%. So there you can see the size is smaller than 247 is smaller than 247. So the small size is take the major part, and the message worker send and receive messages. The message always has a preamble, message, header, so they have the same percentage, 80%, 28%. So it's pretty high, and the other is the OSD operation reply and the OSD OP. So the size is not so big, and the size can tell just only 5 kind of the size. It is pretty simple, but for the 64 kilo read write, we can see here 4 and 20 Y. Yeah. Here the 64 kilo random read is a further read, so it has a metadata to describe the offset and the length which to read. So it will encode it into the read results. So here is some metadata to describe the read result, and there is no big size, as the data read from the Bluestore is discontinuous. And then we analyzed all the thread of the master worker, all the thread of the Ceph OSD, master worker, and the TP OSD DP. So you can see this picture. Yeah, for the 4K random writer, the small size is nearly 80%. It is a major part, and for the big reader, the small size of the CS operation is nearly 15. Yeah. So for the bigger read, we can see the 4K increased dramatically. So, but we did not see 64K read. Yeah, it is because the Bluestore use a fixed size CS unit, no matter how many data reads from the disk. So it is it's not so efficiency. Yeah. So next we analyze the random write operation. For one replica, there is a similar pattern as the random read. Yeah, small size is 85%. Yeah. But for 3 replica, it is more complicated. You can see there is so many different sizes here. But you can see the 80 size equals 28, and the 41 is the preamble and the header. Yeah, it's still occupies 40, maybe near 25. Yeah, but we can see here near about 20%, we have 4, 10, 15. Yeah, this is introduced by the encoder. Yeah. For the 3 replica, we have the replica write operation and the replica write operation reply. So this is caused by the OSD write replica OSD write operation. Yeah, you can see here the master worker send. The buffer list is composed from the small pieces of buffer by encoder. The OSD replica write operation has 10, near about 10 pieces of the buffer list. Yeah, so it occupies nearly 20% of the very small size. Yeah, but for the master worker receiver, they receive the data just in one buffer, so the size is much bigger, and it is a much efficiency CFC operation. Sorry. Okay, we also take the look about all the thread of the 4K rand writer. Yeah. We can see here there is additionally 226 size. It is the page log information, but the similar pattern is the small size is always the major part. Yeah. And for the 64K rand write, we have the same pattern with the rand write, but the difference is the replica write operation data is much bigger. Yeah, here is the same as the rand write. Here is just the same, but for the write read, so the big rand write, the small size of the CSV operation decreased, but always has a very high so the conclusion is that there are many small size CSV operation, and it is not so efficiency. For the 4K and the small size read-write, most of CSV operation is executed by the mesh worker, and the most of the CSV operation size is pretty small. The preamble, mesh header, and the encode process may be introduce many small metadata, just 4, 10, 15 bytes. For the Bluestore, and we can see it use a fixed size. It is not so efficiency. So we do the optimization like this. We do the encoder process optimization, and to avoid the small size, very small size CS operation, and we arrange the data structure to do a more efficiency CSC. And for the highest frequency size preamble mesh header, we just unfold the CS function, use the assembly inline. For the very big read, so we do not need to calculate the chunk by chunk. We just calculate the big size and compare to the chunk size. We get about 2% performance improvement for the 4K rand write. We can see there are so many small size of the CS operation. It means there are many small size buffer here, and it means there are many small size of malloc, memory malloc, and maybe need to memory waste. And there is many discontinuous memory access, it is not efficiency for the CPU cache line. So maybe we can do the further optimization. Thank you.